forward. In this section, we're going to learn about the mean value theorem. Our learning targets for today: find, if possible, the values that satisfy the conclusion of the mean value theorem, write equations for secant lines and tangent lines. We've been doing that all year long. Solve applications involving the mean value theorem and antiderivatives. Ooh, new word. Find local extrema and the intervals on which the function is increasing and decreasing. And then find all possible functions with the given derivative. This we've also found, like that's what we did last section. So it's just in there again, find all possible functions with a given derivative. That is going to involve this new word antiderivative. So first of all, what is the mean value theorem? The mean value theorem says that if a function f is continuous on the closed interval and differentiable on the open interval, then there exists at least one value c in the interval ab such that the derivative equals the slope of that tangent line. So what does this mean? This means if we have a function, let's say the function is this one right here, and it's going from a to b, there's a tangent line there connecting, or there's a secant line connecting the endpoints. What this says is that somewhere in between there's going to be a point where the tangent line has that same slope. That's all it says. In practical application, if I'm driving to town, it takes me half an hour to go 22 miles. That means I'm driving at 44 miles an hour. Assuming that my speed is differentiable, so there's no sudden stops or starts, it's just kind of smooth, the speed goes up, the speed goes down, there's at least one moment in time from my house to the school that I am driving at exactly 44 miles an hour. Chances are there's more than one in this situation, but that's what it means. At some point in time, it will be the average, your average rate of change, and your instantaneous rate of change will be equal. But again, that's assuming we need it continuous on the closed interval, so that includes the endpoints, and differentiable on the open interval. So that's what the mean value theorem says. One of the biggest mistakes, confusions, is getting it confused with the intermediate value theorem that we saw before. The intermediate value theorem, notice it looks very similar. F of x is continuous on a closed interval, and then m is between there. Then there exists a number c in the middle such that f of c equals m. So here we have continuous on a closed interval, and we have a c in the middle such that f prime of c equals something. The intermediate value theorem is looking at y values. It says that somewhere between here and here, it's going to hit this value in the middle. So the intermediate value theorem is looking at y values. The mean value theorem is looking at slopes. Now, if we had a function, we took a derivative. The derivative is the slopes, and they also become the y values. So, I mean, it is possible to use one instead of the other, but ideally, intermediate value theorem is y values. Mean value theorem is looking at slopes. So let's see how this works. So we have our mean value theorem here still. We want to find the points where it's going to, the points where the tangent will equal the secant. So first thing, we have to satisfy the conditions. So it needs to be continuous on a closed interval, 0 to 1. Well, x squared plus 2x minus 1 is a polynomial. It's always continuous. And differentiable on the open interval. Well, it's a polynomial, so it's always differentiable. We don't have any kind of cusp or corner or anything like that. So we need to figure out what that secant slope is. So we have 0 and 1. We need to find f of 0, and we'll need to find f of 1. F of 0, we plug in 0, well, that's -1. Plug in 1, we get 1 squared is 1, plus 2 is 3, minus 1 is 2. So now we need the slope in between there. So that's going to be 2 minus -1 over 1 minus 0. So 2 minus -1 is 3 over 1. So that slope is 3. So this f of b minus f of a over b minus a equals 3. So that means somewhere the derivative will equal 3. So we're going to find the derivative. F prime of x is 2x plus 2. And we just need that to equal 3 somewhere. We can subtract the 2 to get 1 equals 2x. And so it's at x equals 1/2. And notice that 1/2 is in between there. We can make the equation of the tangent line. We have our slope is 3. The point is 1/2 comma, plug it into the original function, figure out whatever the other point is. And we've done tangent lines. You need a slope and a point. We could do the equation of the secant line. The slope is 3, and you can use either of these 2 points, either 0, -1, or 1, 2, and the slope is 3. But the important part here is, hey, we can find first that we check the conditions, and then we found the slope, and then we could even find the x values in the middle that works. So let's look at another one. We have f of x equals 1 minus x squared on -1 to 1. So here we do have some possible issues. It has to be continuous on the closed interval. Well, the underneath the square root has to be positive. It'll be positive in between -1 and 1, or 0. It has to be greater than or equal to 0, and that'll happen in between -1 and 1, so that works. If we had anything outside of -1 and 1, like if it was from -1 to 2, that doesn't work. That's actually not even in the domain of the function. And then differentiable. So if we graph this, we actually see that this is a half circle, which is differentiable. There's nothing weird that'll happen in between there. So we need to find the slopes. So if we plug in f of -1, we get the square root of 1 minus -1 squared. 1 minus 1 is 0. And f of +1 also equals 0. The slope 0 minus 0 over 2. So our slope here is 0. Okay. And so at some point, the derivative has to equal 0. So our derivative, f prime of x, so this is all this to the 1/2, because that's what the square root does. So we'll have 1/2 times 1 minus x squared to the -1/2, and then times the derivative of the inside. We have some chain rule, -2x. So we could rewrite this. 1/2 times 2 goes away, so we'll have -x over the square root of 1 minus x squared. We need this to equal 0. Square root of 1 minus x squared. It equals 0, a fraction equals 0 when the numerator equals 0. So this will be when x equals 0, which, being that it's a semicircle centered at the origin, and we're looking for the horizontal tangent, it would be at the top, so that makes sense. This particular application, when these two things are equal, is called Rolle's theorem. I don't know why it does that. It's called Rolle's theorem. It's just an application of the mean value theorem where when f of a equals f of b, then at some point the derivative will equal 0. I kind of surprised that that got named after someone. He's the first person that proved it with polynomials only. He didn't even prove the full thing. But whatever, it got named after him. So if f of a equals f of b, then at some point in between there, the derivative will be 0. Again, assuming that it's differentiable and continuous. So one last one I wanted to show you. I'm going to have to erase this random line that showed up there. That was weird. Maybe I can put the L back. There we go. So one last one, and this looks a lot like the first one we did. So we can plug in our values. F of 0 is going to be -5. F of 3. Oh, it's a polynomial, so it's continuous, it's differentiable. We don't have to worry about that. F of 3, we have 27 minus 27 plus 6 minus 5. So that's going to just be 1. So our slope here, we're going to have 1 minus -5 over 3 minus 0. So that 6 over 3 is 2 is going to be the slope. So somewhere that derivative is going to have to equal 2. So let's see, that's going to be 3x squared minus 6x plus 2. So we can set that equal to 2 equals 3x squared minus 6x plus 2. Subtract that 2 over to get it equal to 0, because that's how we solve quadratics or any other polynomial. So we get 3x squared minus 6x, the 2's cancel. So we can now factor in 3x out of this. And so we have 3x times x minus 2. So that means that x could equal 0 or x could equal 2. Now, there's actually only one place here that is told to us by the mean value theorem. Now, the mean value theorem doesn't always say one place, but I'm using this example specifically because the mean value theorem says that there exists at least one value c in the interval AB, this open interval. So it's from 0 to 3. So 0, that doesn't work for the mean value theorem. Yes, the slope is still equal to that. That's fine. It could be equal to that on places outside of our interval as much as it wants as well. We don't know anything outside of our interval, but what it says is that somewhere in between 0 and 3, the slope will equal 2. And that happens at x equals 2. Again, at x equals 0, the slope also equals 2, but that's not what the mean value theorem is telling us. It's looking for the one in between those two values. And again, it could have been 1 and 2. That would have been fine. We would have had 2 of them. But in this case, the 0 doesn't match the mean value theorem. Oh, I forgot to fade that one in. Oh well. So increasing and decreasing functions, we've seen these. The definition, it's increasing if every x value, or for when x values get bigger, the y values get bigger, right? It's going up. It's decreasing if it's going down. When the x values get bigger, the y values get smaller. And it can be increasing or decreasing on intervals. We saw that last section when we were looking at finding the extrema. We made our sign tables. Nope, that was supposed to be a plus. Hey, it was positive here, negative here, positive here. And so this one would be a maximum, this one would be a minimum. Well, that part of the domain, it's increasing. In the middle, it's decreasing. And here it's increasing because the slope is positive, the slope is negative, the slope is positive. And that's what this first corollary says. It's increasing if the derivative is positive for any point on the interval. It's decreasing if the derivative is negative for any point on the interval. And this is a corollary. A corollary is a thing, it's not quite a theorem, but it's something that's really easily proven by a theorem or by a definition. And so this could be really easily proven using the mean value theorem. And then a second corollary, functions with f prime equals 0 are constant. So if we take the derivative and we get 0, that means it was just a number. It's a constant. It means the slope was 0 the whole time. It was a horizontal line. And then functions with the same derivative differ by a constant. So what is that? So if we have, say, y equals x squared, the derivative, y prime, equals 2x. Well, we could have y equals x squared plus 2, which means y prime equals 2x. So this plus 2, that could be plus any number, and it's not, it's plus any number, and when we take the derivative, we're not going to see it. And so that's going to come into the antiderivative. Antiderivative is just going backwards. What gave us this derivative? So if we knew that the antiderivative, so in this case, the antiderivative is going to be little f of x. The derivative is, come on, pen, right, little f of x was the derivative. Let's say it was 3x squared. Well, what would give us the derivative of 3x squared? F of x would be x cubed would give us that derivative. This is going to be a huge, whole couple chapters of stuff that we're going to be doing. This is just a little introduction. The key here is not only x cubed, like x cubed plus 1, x cubed plus 2, x cubed minus 7, x cubed plus c. We have an unknown constant that has to go on the end of that, and it always has to be there when we take an antiderivative. And so it's just thinking what would give us this derivative, and then go backwards from that. So this is the section. It's mostly mean value theorem stuff. This is a little piece. But I'll see you in class. Until then, keep working problems, keep asking questions, and as always, happy mathing.